Okay, so today I'm going to cover, still in chapter 1. Now I'm going to cover part 2 of chapter 1, which is instrument performance and statistical analysis. Okay, so you should see the second slide right now, which is the learning outcome. What is expected after you finish this class today with me? So there are 4 learning outcomes. Number 1, you should be able to explain about the static and dynamic characteristics of measurement. Okay, apa tu? What is static and dynamic? Okay, we'll talk about it afterwards. And then number 2, describe about the errors that can occur in measurement. And then number 3, calculate basic error parameters. And then number 4, apply basic statistical analysis principles to verify measurement results. So these are the 4 objectives that I have set for you to achieve by the end of the lecture. Okay, so instrument performance characteristics. So when we talk about instrument performance, basically it can be divided into 2. Number 1 is static, and number 2 is dynamic. So our focus now is going to be on static condition, where we want to measure a value under steady state process condition or constant process condition. Now, these characteristics are determined or are used to determine what is the most suitable instrument for a specific measuring task. So we are going to look at these 11 criteria of static characteristics. I know you have studied or have seen this all before, so this is more of like a review. So we are going to look at accuracy, precision, tolerance, range, linearity, sensitivity of measurement, threshold, resolution, sensitivity to disturbance, hysteresis, and dead space. Okay. Don't worry too much about memorizing everything. As long as you understand what are the characteristics all about, then I believe you can apply common sense and logic to determine the characteristics. Okay, accuracy. So when we talk about instrument accuracy, we are talking about how close the result of our measurement or the output of our reading to the correct value. So these are the first few equations that you see. These are very simple equations that we use to determine the accuracy. So we can determine the accuracy either in absolute value or relative value. And we can also determine accuracy as a form of error. That means the error is correlated to accuracy. Once you know the error, then you know what is the corresponding accuracy because it's complement each other. Okay, so we have the first equation, the error, absolute error is equal to this equation here, yn minus xn, where yn is the expected value and xn is the measured value. And then we apply this relationship to determine the percent error. And then the relative accuracy, capital A, and then the percent accuracy, small letter a. Let's look at that simple example. So given that the expected value of the resistor is 80 ohms, and the measurement recorded is 79 ohms, so calculate the following parameters: absolute error, percent of error, relative accuracy, and percent of accuracy. So the answer is given in the next slide. So the absolute error is simply the value of yn minus xn, which is what is the expected value minus the measured value. So you have 80 minus 79, you get 1 ohm. Okay. And then for the percent error, we have 80 minus 79, we divide by the expected value 80 and then we multiply by 100% to get 1.25%. If your expected value is lower than your measured value, let's say you have 79 minus 80, then you get minus 1. But because we have modulus here, we convert all the negative values into positive values. Okay, basically we have modulus to convert all the negative to positive values because we are not concerned about the polarity or the sign. We just want to know the absolute value. So relative accuracy, we have this equation here, 79 over 80. We get 0.9875. And then percent accuracy, we get simply multiply the value of relative accuracy by 100%. So you get 98.75%. Or you can have 100% minus the error. You also get the same value, 98.75%. So this is the accuracy that we are talking about. The closer we are to the value of 100%, that means the more accurate our reading is. Okay, so the idea is to identify what are our errors and how to minimize them, which we will look into after this. Okay, the next criteria is precision. So precision, we are talking about a measure of consistency or repeatability of measurement. Basically, this means that if you measure a parameter, you get a certain value, and then you do another measurement, you should get similar or near to the value that you just measured. So if you repeat the same measurement, you should get around the same values. So if this happens, that means the equipment is precise. It can measure with confidence. When you repeat the measurement, the result will be around about the same. So we are introduced to another equation where we can calculate the precision using this equation here. So we have xn minus xn bar, where n here refers to the value of the reading, and then we minus with the x bar here refers to the average value. Okay, so for example, let's look at this table here. So this table, we have 10 readings of a certain value, right? And the value ranges. When the measurement is taken the first time, you get the value as 98. When you take it the second time, it's 101. So you repeat the measurement 10 times, these are the 10 values that you get on the measurement value. So it's around the same values, but it's not exactly the same. So in order to calculate, now the question asks, what is the precision of the sixth measurement? So you refer to the table, the sixth measurement, the reading is 100. So we apply the equation. First, we calculate the average. The average is the sum of this whole table, which is given as 1005, and we divide with the number of reading or number of measurement, which is 10. So we get the average is 100.5. So to determine the precision of the sixth reading, we replace x6, which is 100, and then we minus with the average, and then we simplify this equation to get a value of 0.995. So that is the precision of the sixth reading. And we can do the same thing for each type of reading, and we'll get what is the precision value. Okay, so basically here, precision refers to how close the value is with the average value. The closer it is to the average value, that means it's more precise. All right. So accuracy and precision is interrelated. So you can see this simple diagram that describes the relationship between accuracy and precision. So here, the first one here, when you have accurate and precise, that means the reading is close to the center value and all the readings are clustered nearby. So it's accurate and precise. If you look here on the right side, so you have the condition where the reading is precise. All the values are clustered together. That means every time you repeat the same value, every time you repeat the reading, you get around the same value. But actually, it is not located close to the expected value. So we call this as systematic error. Okay, we look into error after this. The bottom one here, the third condition, we have the value that is roughly accurate, which is it's centered around the center value or the true value, but it's not precise because the values, when you take different reading, it is quite far away from each other. So that means it's not precise. And the final condition, it's both not accurate and not precise because the reading is quite far away from each other and it's not close to the center value, which is the true value. Okay, so what is the importance of accuracy and precision? Now let me share with you one of the application where accuracy and precision is very important. I'm going to share with you now a video from YouTube from Omega, which is the official timekeeper for the Olympics, on how they time the 100-meter sprint. So you can see the video in YouTube later. So I just want to share with you. This is the current standard of measurement for 100 meters. Okay, so now they use electronic starting gun. They have the false start detection system and they have the starting block, right? So the starting block has sensors installed. So the system will signal a false start if the equipment detects a reaction less than 100 milliseconds. That means if you move faster than the gun, then it's going to trigger the false start. Okay, somebody is turning on the mic. Do you have any question? Okay, thank you. Now, previously, if you during my younger days in the 90s, early 2000, they use a human to detect the false start. But human eye is usually not reliable because they may not detect the small changes in time. Now they use sensors and will automatically trigger false start sensor if they move faster than the gun, even by 100 millisecond. Okay, and you can see at the back here, it has every runner has their own speaker so that they can hear the sound of the gun at the same time. Okay, if you look previously in the sorry, this is the wrong. Okay, previously the gun is not electronic. They use an actual gun. So the one sitting closer to the gun will hear the gun faster than the one further away from the gun. So the person staying at lane 1 will hear the gun faster than the one running at lane 8. So now they have separate speakers for each runner so that they can hear the sound of the gun at the same time. Okay, so when After the runner completes the running, okay, photo cells stops the running time on the TV and scoreboard, and you see here that the camera captures 10,000 images per second of the finish line. Can you imagine 10,000 images per second? Because 100 meter, right? Everyone is fast. They need to capture a lot of images so that they can verify the winner conclusively. So 10,000 images per second, and they use it to generate the photo finish picture. That is the level of detail in terms of precision and accuracy that is required in 100 meter time measurement. Okay, coming back. So we have tolerance. This is the third item for static characteristic. So we have accuracy, precision, now we have tolerance. So tolerance basically gives you roughly the range, or what is the expected level of accuracy for your reading. So for example, if you have 100 plus ohms, plus minus 5%. So basically you have the value of the reading should be around 5% of 100 ohms. So when you measure, this one is resistance, when you measure, the range should be between 95 and 105. So if you do the measurement of the resistance using the meter, and suddenly you find out that the value is out of this range. Let's say you measure, suddenly you find the value is 90 ohms, not 95. So then you know that the error is not coming from the equipment, from the measurement itself. There must be something else that is causing the error. Okay, so this is important when you want to verify your reading in your experiment, in your project reports and everything. You need to verify whether the measurement is correct or not, whether it complies to the standard of the equipment or the parameter you are measuring. Okay, sometimes the tolerance has a different upper value and lower value. So for example, like a single phase supply for electricity. So the standard range is given as 230 volts, but it's plus 10% minus 6%. So when you measure the range of the voltage for your power supply, single phase, should be around this value, between 216 to 253. Okay, tolerance and range are related. So basically, range defines the minimum and maximum values of a quantity that the instrument is designed to measure. So we need to select an instrument that matches the range of the parameters that we want to measure. If it is out of range, then you may get the wrong reading, or you may have a error when you read the value. At worst condition, you may damage the instrument. When you measure, when the actual value is higher than the maximum value of the instrument, of the measuring instrument. So the range must match the quantity we want to measure. And then number 5 is linearity. So linearity basically means that we ideally want, when the value of the parameter that we measure increases, then the instrument will also increase proportionally. So if it decreases, it's also decrease proportionally. So a linear change will make the reading more easy to understand. Okay, so linearity. And then 1.6 is sensitivity of measurement. So sensitivity refers to how much the instrument changes when the quantity changes. So when the quantity we want to measure increases, the instrument changes significantly, then we say that the instrument is more sensitive. So for sensitivity, the equation is given as the scale deflection divided by the value of the measurement producing deflection. So as an example, we look at this simple table. So we see that it's a measure between resistance and temperature increase. So they measure the resistance of a platinum material at different temperature ranges, and they find the following correlation. So we can see from this table that there is a correlation, which is for every 30 degrees increase in temperature, we have 7 ohms increase in resistance. So as the temperature increases, the resistance also increases. And we can say that the increment is linear, because here, when it increases 30 degrees, the resistance increases 7 ohms. When it increases another 30 degrees, it also increases another 7 ohms in resistance. So this is number one, linearity. The scale of change is the same. And number two is sensitivity. So to determine sensitivity, simply we have 7 divided by 30, and the sensitivity is 0.33 ohms per degree Celsius. This is the sensitivity. So generally, the larger the value here, that means the more sensitive the equipment is. Okay, I repeat, the larger the value that you obtain here, the more sensitive the equipment that you are using to measure. Okay, next point is threshold. So when we talk about threshold, threshold is the minimum level before the measuring instrument starts to measure. Okay, we can see from the figure here that the threshold value, when you use a measuring instrument, sometimes it does not start instantaneously at 0. It requires a certain value first. After this value here, only then it starts to measure. So this gap here, we call it as threshold value, the minimum level before the instrument starts to measure. So this is the starting point. The range between 0 to this point is called the threshold. Okay, that will depend on the equipment. Later on, when we see the equipment, you will understand more about threshold values. And then resolution. So resolution is quite intuitive. I know you already know about this. It refers to the smallest change that can be measured. So a simple example are the two rulers here. So one, we only have the scale up to centimeter, and the other one, we have the scale up to millimeter. So by using the second one, ruler B, we can identify the length of this candy to be more precise. We can get it until a few millimeters, and we have a smaller range of tolerance compared to this one, where we can only estimate roughly what are the value in centimeters. Okay, so maybe we can assume in this example, we can take it as 4.2 centimeters if you use ruler A. Okay, 4.2 centimeters, but here you can be a little bit more accurate. Maybe you can say it's around 4.25 centimeter. Okay. And then the next point, point number 9, is sensitivity to disturbance. Okay, so sensitivity to disturbance, it basically means there might be some other external parameters that affect your measurement. For example, if you are using an analog weighing scale, you nak timbang berat, you want to weigh your weight, and you use an analog scale, you have to make sure that the dial is pointing directly at 0. If you use the weighing scale, after some time, it will have some drift. The value will not stay at 0. Maybe it will going to be shifted a bit to the left or to the right. So you see the figure on the left hand side. This refers to when you have a consistent drift. That means, for example, the weighing scale, if you do not do the calibration correctly, then it may have a value before you weigh your, before you do your weight, you measure your weight. So the actual value should be the dotted line, but because of the sensitivity to disturbance, because of the error of the weighing scale, then it's going to show a wrong value, which is indicated by this solid line here. Okay, so this refers to what we call as zero drift. The second condition is what we call as sensitivity drift. So sensitivity drift, sometimes when you use cheap meters to measure certain measurement, so the larger the value that you measure, the more it deviates from the actual value. When you measure small value, for example, then the value will not be too far away from the correct value, from the true value. But as your measurement increases, then the error starts to increase as well. So we call this as sensitivity drift. And the third condition is a combination between zero drift and sensitivity drift. So the reading, the actual one, and the reading that you get will be even more further away. And this will introduce error in your measurement that you need to identify. Okay, the 10th point of static condition is hysteresis. Now, hysteresis is a bit complicated. If you are taking electrical subjects or mechanical subjects related to springs, dynamic motion, you will see this kind of pattern. What this basically means is that in ideal condition, when you increase a certain amount of value, then it's going to increase the output reading. And by right, when you reduce the reading back to zero, then the reading should go back to zero. That is the ideal case. But here, let's say you start at this point here. When you increase the value, then okay, you are going to have an increase in the output reading. You follow this curve here. But then when you reduce the value of the reading, then suddenly it follows a different path. It doesn't go back to the original path, it goes a different path. So you have a different reading when you reverse the process. So we call this as hysteresis when measurement is affected by past history. Okay, for example, when you use spring, once you stretch your spring, after stretching so many times, after some time the spring will lose its elasticity. And when you measure the spring, then the level of strain and stress will be different every time you stretch them. So this is example of hysteresis. And then the final point is dead space. So dead space is the range in between where there is no change in output value. Like example in the figure here, when you start to measure, okay, it reaches a certain value, but suddenly at this point here, it loses the reading. There is no change. Even if you increase the value, the reading will still be the same. Only after a certain point, then it starts to increase again. So this is different from threshold. So if I go back, so threshold is the minimum starting point. Threshold is the minimum starting point before the instrument can start to measure. But dead space is actually the instrument can measure, but it loses the value at a certain duration of the reading. So the area here, we call it as dead space. Okay, so those are the 11 criteria for static characteristics in instrument performance. Okay. So now I would like to move into the types of static errors. So before I start to go on this topic, we'll take a short 5-minute break. And if you have any questions, please put them in the meeting chat. Okay, meanwhile, for BMFG and BMFI students, you can also access YouLearn now and record your attendance. For BEKG direct entry students, your attendance is not available yet. So you don't have to register because I don't think it's in the list. But it's okay. We'll start to take your attendance from next week. Okay, so we have a short 5-minute break and then I'm going to move towards the types of errors. So far no question, yeah? If there are, yeah.
Still cannot access, sir.
What do you mean?
Attendance.
Oh, can I access? Okay, hold on. I didn't hide this, so you should be able to see it. Let me see. Okay, can you please try now?
Doktor tak boleh tekan lah doktor.
Tak boleh? Okay, hold on. Okay, cuba lagi sekali.
Okay, sir. Dapat sudah, sir.
Saya dapat?
Dapat sudah, dapat.
Okay, bagus. So status P lah, present. Okay. So now I'm going to proceed with the types of static errors. Okay, so there are basically three types of errors that you need to know. Number one is gross error, number two is systematic error, and number three is random error. So gross error is basically human mistake. Systematic error is error caused by the instrument. And random error is error that we do not know the actual reason why it happens. That's why we can call it as random. So under systematic error, it can be further classified into three types, either instrumental error, environmental error, or observational error. And then we have the other three, which is we'll look into it afterwards. But let's look at the main item now first. So gross error is mainly due to human mistake. So basically gross error and human error is the same. Okay. So when we talk about human error, macam-macam. We talk about reading the value. Kadang-kadang you guna salah scale. You use the wrong scale for your measurement. Or you miss a decimal point when you write down the result. Or you use the equipment wrongly, incorrectly. Or you use the range incorrectly. So many human mistakes can occur, and this we call it as gross error. So gross error can usually be minimized by being careful when taking measurement. Okay, and this is why it's good practice whenever you do measurement, you don't do it alone. You do it in groups, at least with a partner. Okay. In real life, even now, if you go for engineering, if you go for measurement, usually they assign you in pairs so that you make sure that you take the correct reading and you have somebody else to verify that your reading is correct. Right? So this is one of the things that can be done. You do measurement carefully, you do it in groups, and you conduct measurement at least 3 times so that you make sure that you get the same value or around the same value each time. If you take measurement only once, then you are prone to making human mistakes, getting the wrong value. And it's also good knowledge or good practice to know what is the actual range that you are measuring, so that when you measure, you know that whether the value is logical or not. Okay, so gross error is related to human mistakes. Now, systematic errors. So systematic errors refer to the instrument. So the instrument can be, the error from the instrument can be because of the instrument itself, or can be because of other factors affecting the instrument. So systematic errors are predictable errors. They always affect the reading by the same amount or proportion. Okay, kalau the instrument is faulty, if the instrument is faulty, when you measure, you get certain value. You measure again, you still get around the same value. So sometimes it's also referred to as bias. So bias means it's always biased to be measured at around the same value, which is not the correct value. And it influences all the measurements of a quantity alike. Right? So the example I gave you just now about the weighing scale. Let's say the scale has an error of 1 kilogram. So if you weigh yourself, then the error will be plus 1 kilogram to the minus 1 kilogram to the actual value that you measure. So if you do the measurement again, you repeat the same measurement, you still get the same type of error of 1 kilogram because of the systematic error of the weighing scale itself. So this is what I'm talking about, always affect the reading by the same amount of proportion. So if somebody else is measuring the weight using the same scale, it's also going to be biased by 1 kilogram or affected by 1 kilogram error due to that problem. Okay, it can be further divided into three types, either instrumental error, environmental error, or observational error. So instrumental error is caused by instrument limitation. Okay, so many things can cause instrument error. So examples include friction in bearings if you measure like torsion or speed of motor. So irregular spring tension when you want to measure the force of a mechanical equipment. And then thermal effects of components, right? When you want to measure something, let's say you want to measure a temperature of a machine, but there are other machines nearby, and the other machines are also producing heat. So it may affect the temperature of the machine that you are measuring and give you the wrong value. So it can be avoided by, these are just a few examples. Number one, properly selecting a suitable instrument, applying correction factor, and then we need to calibrate the instrument periodically against a standard, which is what I covered in our lecture last week. Okay, another type of systematic error is coming from environmental error. So external condition that affect the measuring device. Okay, this is the example that I gave just now. Temperature reading of a machine may be affected by heat from other equipment nearby. And these errors can be avoided by removing the effect of the external condition or shielding the device. And the third type is observational error. So observational error is usually introduced by the observer. The most common one you learn probably in secondary school when you do your lab reports is parallax error. So you don't measure the value correctly, resulting in a different reading. Okay, so in this example here, you see that it's related to the position of your eyes when you measure the scale to determine the level of the liquid. Okay, but there are also other types of observational error. For example, if you use or you read the wrong scale, maybe here it's in millimeters, but you mistakenly take in centimeters, then the value is going to be different. Okay, observational error. And then finally, for the types of error, we have random errors. So these random errors are errors due to unknown causes. It's normally small. So basically, this is what happens when you measure a certain parameter multiple times. Even though the condition is exactly the same, the meter is exactly the same, you use the same method, the value will differ a bit by a certain value when you take multiple reading. So there will be still some variation in your reading, even if you control all the other parameters. So this is attributed to random errors, which you cannot control. Okay, these are the sources of error, possible sources of error. It can be from insufficient knowledge of the process parameters and design conditions. It can come from the poor design. When you do the measurement, the design of the measurement itself is poor. It can come from a sudden change in process parameters or irregularities that you did not detect. It can be from poor maintenance. Okay, the equipment or the measuring instrument is not properly maintained. Okay, error caused by the person operating the equipment and design limitations. So these are possible examples of sources of error. So that is what static characteristic is all about. Okay, now we move into dynamic characteristics. So dynamic characteristic is when you do a measurement, there is usually a time delay between the measurement and obtaining the reading. So because many quantities fluctuate with time or have transient condition. So there is a gap between the value when you want to measure something. There is a gap between when you start to measure and when the value becomes stable. Okay, so there are three common variation in measured quantity. Number one is step change. So for step change, you refer to the top figure here. So for the step change, maybe you start at 0, but suddenly after a certain point in time, it raises to A. So there is a sudden change from 0 to A at this point here. So this process or this change is called as step change. The second condition or the second situation is linear change. So linear change is common. When you increase the certain value, then the corresponding value here will also increase. So we have a straight line here. This is called a linear change. Okay, so the sensor measures the variable, it changes linear with respect to time. And the third one is the probably most complicated one, when you have sinusoidal change. Okay, so for BMFG and BMFI students, you need to recall back what you have learned in Principle of Electrics and Electronics or about the AC waveform. Okay, so we have sinusoidal waveform, so we need to know how to analyze these values here. So these are the three most common variations. And when we talk about dynamic characteristics, there are four features that we need to know about. So number one is the speed of response. How fast the instrument responds to changes. And then number two is fidelity. Fidelity means basically how reliable your measured quantity with the actual result. Okay, so the degree or how accurate the instrument can detect the changes of the measured quantity. That we call it as fidelity. And then the third factor is lag, the delay between the measurement and when the value comes out. Okay, the longer the delay, then the more unreliable the result. And then finally, dynamic error. So dynamic means changes with time. So dynamic error, the difference between the true value and the actual value when there is a difference in time. Okay, so these are the four dynamic characteristics. Okay, so now I've covered about the static and dynamic conditions of errors. So the next part, I want to move into statistical analysis. So you have done your reading, you have identified the errors. So let's say you have already minimized all your you do experiment in the lab, right? For example, and then you have already minimized all the errors. You make sure you don't do any mistakes when you do the reading. And then you already identified whether there are any systematic errors when you do the measurement. So you try to be as accurate and as precise as possible. Now, when you do the measurement, you have data. So you need to analyze the data to understand what your results mean. Okay, I see this pattern usually in lab reports. When you do your experiments, there is always a part where you need to discuss your results. In your report, there's a section discussion. So you need to discuss the results. So many students do not understand what is expected from the lab report itself. So all they discuss is whether the result is accurate or not, what are the possible errors, and usually they always write parallax error. Okay, the difference is because of parallax error, wrong reading, even though they are reading using a digital meter. So hopefully, by going into this basic statistical analysis, you have more understanding on when you have a data, what does the data mean? And how you can use the data to make decision, whether your experiment is correct or not, whether the result is reliable or not. Okay, so statistical analysis is used to basically analyze your data and to identify whether there are certain patterns that you can see, or certain errors that you can identify. Okay, so by using statistical analysis, you can use it to minimize random errors, but it cannot remove systematic errors, because systematic errors is the error coming from the instrument itself, or the environment, or the observer. So if it's the same source of mistake, you cannot remove it from statistical analysis. Okay. So time now is 11:55. Okay, I'm not going to take long, maybe around 20 minutes more, and then I'm going to wrap up this class session. Okay, arithmetic mean. Purata, simple lah, straightforward. You get a total of the reading and you divide by the number of reading, which is given here. Okay, this is arithmetic mean. This is the basic statistical value that we want to determine usually from our data set. And then the second one is deviation from the mean. So we want to know for each value, how far is it from the average value? Okay, so we have, for example here, deviation 1, reading number 1 minus the average. So deviation number 2, reading number 2 minus the average. So we want to know how far is the value, is each value from their average value. Okay. So this is the example. So we have an object measured in millimeters. It's measured 5 times. And you get the following values here. So you want to determine the arithmetic mean, deviation of each value, and the algebraic sum of the deviation. So the simplest way of us to do this and to make sure we don't make mistake is by doing a table. Okay, so we record the reading in a table. So we have these 5 readings and this is the corresponding value for the reading. So to find the average, we sum all the values and then divide by the number of reading. So in this case, we get the arithmetic mean as 49.86. And then to determine the deviation of each value, we minus each of the reading with the average value. So we get a value of, for example, here, the first reading, we get negative 0.16 and so on until the 5th reading. And the third one, the algebraic sum of the deviation, that means we sum all these deviations together. So when we sum them, negative plus positive plus positive plus negative, the total should be 0. So this is how you solve using arithmetic mean and deviation of each value. Okay, next is the average deviation. So average deviation is to determine how precise the instrument is when you do the measurement. So if the instrument is highly precise, then you should have lower average deviation value. So basically it's the sum of the positive value of the deviation divided by the total number of reading. Okay. So this is the example just now. So calculate the average deviation for the data given. In example 1.3, so we put all the deviation here, negative 0.16, 0.24, and so on. And we convert the negative value into absolute values. We convert them all into positive values. And then we divide them by the number of reading, which is 5. We get 0.232. So the average deviation is this value. The lower the value here is, the more precise the equipment. Okay, then we have standard deviation. This is the most important parameter that is used in statistical analysis. Okay, so standard deviation is a measure of the amount of variation of dispersion, how far the data is spread over its average, over its mean. So a low standard deviation indicates that the values tend to be close to the mean. A high standard deviation, that means the values are spread wider apart. So we use this equation here, which is basically the deviation. We square it, we sum all the values, divide by the number of reading, minus 1, and then square root. So we have two equations. If the number of reading is less than 30, then the denominator we use as n minus 1. If n is equal or more than 30, we use divide by n. This example of standard deviation. So let's say the average or the mean is 100. If you have the standard deviation equals to 5, then you have this blue line here. So that means the data, when you do multiple reading, the data are closer to each other. It only falls around this curve here. So the data is very close to each other. So we call it as quite precise data with low standard deviation. If you have sigma equals to 10, the average is still 100, but you see now the range is bigger. The range is larger. The data is spread out compared to sigma equals to 5. And you have sigma equals to 20, then it's more flat. The average is still 100, the mean is still 100, but because the dispersion is more, so the data tends to be spread out. So based on our measurement, we will know what kind of data that we are dealing with. Okay, so using the same example as 1.3, calculate the standard deviation. So this first 3 column was what we get from example 1.3. Now we want to calculate the standard deviation. So standard deviation, basically what we do is we take the deviation and we square it. So all the values we square, we get these values here on the right hand side. And then we add them together to get 0.292. Right? So then we apply the equation for the standard deviation. So we have, this is the sum of the square root. When we square root each value, we get this value. And then when we sum all the square root, we get 0.292. So now we can replace this value in this part here. We have 0.292. Because it's only 5 reading, so we use n minus 1. So we get this result here is 0.27. So that means the value is, the average is 49.86 and the standard deviation is plus minus 0.27. Okay, and then standard deviation is also used to measure confidence in statistical conclusion. So we have what we call in normal distribution, when you do multiple measurement, you should get a normal distribution, something like this. A simple example is when you do exam for your subject. Now, when you do the exam, in general, many of you will get around average marks, let's say B. So B will be the center point here. So some of you will score B+. Some of you will score A-, and a small percentage will score A. Similarly, some of you will score, most of you will score maybe around B-, and then a few C+, C-, and then D, and then some of you may fail. But as you go further, it should be the amount of students that either gets A or fail should be smaller than those students who get around average marks, B+, B-, and so on. So this is the normal distribution. So most will tend to be around the average value, only a few will be distributed away from the values. So standard deviation is also used to measure confidence in statistical conclusion. So we have here what we call as 68, 95, 99.7% rule. So if you measure multiple times, you'll see that 68% of the data should lie on this range, around this range, plus minus 1 standard deviation from the mean value. 95% of the data will be plus minus 2 sigma or 2 standard deviation from the average value. And almost 100% will be within 3 standard deviation of the average value. Okay, to understand better, let's look at this example. So the normal distribution below is obtained after doing 1000 measurement. Okay, so you have 1000 measurements, so you have this normal distribution here. If the standard deviation is equal to 10, what is the percentage of data that falls between 70 and 90? So by right, you should understand from this data that 70 is the mean, the arithmetic mean. Okay, so we are interested in finding from the 1000 measurement, how many measurement fall between 70 and 90. So we know that if the standard deviation is 10, so that means now we know that 70 is the center point. So plus 10, plus another 10, we get 70 to 90. And then we have minus 10, and then minus another 10, so we get to 50. So basically, this is 70 plus sigma plus 2 sigma. And then this is 70 minus sigma minus 2 sigma. By referring to the figure here, we know that when we have plus minus 2 sigma, it's equal to 95% of the data. So coming back, we have 95% of the data here. Because we are only interested in finding the value between 70 and 90, so it's actually half of 95, which is 47.5. That means from 1000 of your measurement, around 475 of the reading should fall somewhere around this area between 70 and 90. That is the general idea of standard deviation. And then distribution of measurement. Okay, so let's see this example here. So voltage across a resistor is measured 51 times. And the results are given in the following table. So we want to analyze the data using basic statistical analysis. So the measurement is done 51 times. So this is the record. When it they measured 1.01 volt only once. There are 3 times when they get measurement of 1.02. 6 times the measurement 1.03. There are 10 times when they measure they get a value of 1.05 and so on, so on. So the total number of reading is 51. Then we calculate what is the total number of from each reading. So 1.01 multiplied by 1, we get 1.01. 1.02 multiplied by 3 numbers of reading, we get 3.06. So we multiply each of the value with the number of times that the value occurs to get the total sum of the value, and we add them together to get this total value 53.75. And then we can divide this value 53.75 with the number of measurement 51 to get the average value, which is what you get here, 1.054 volts. This is the average value. And then we can also determine the average deviation. So the average deviation, we find the individual deviation for each value, and then we determine the absolute value together with the number of measurement. So for example, here the reading is negative 0.03. There are 3 readings, so 3 multiplied by 0.03, you get 0.09, and you convert into absolute values to get positive. So you get all positive values and you add them together to get 0.86. And then you divide by the number of reading to get the average deviation, 0.0168. And then similarly, you repeat the process for standard deviation to get the value as 2.142 times 10 to the power of minus 2. Okay, by utilizing this value here. 234 times 10 to the power of minus 4 divided by the number of reading 51. So you get this value here. And you can roughly draw the figure. So the solid line refers to the ideal curve, normal distribution, but the slightly thinner line represents the ideal, the actual curve from the 51 measurement. The more measurement you do, let's say you repeat the process a few more times, the more smooth the actual curve will be. But because this is only 51 times, so we'll see that the actual curve is a bit different from the ideal curve. Okay, so we have the mean is 1.054, the value that we calculated just now. And then we have a standard deviation of the previous value just now times 10 to the power of minus 2. Okay, so a bit more, a few more slides. I want to cover about limiting error and summation of error. Okay, so limiting error is basically refer to the full scale reading. So most measuring instrument specify accuracy within a certain percent of full scale reading. For example, plus minus 2% of full scale detection. So we call this as limiting error. Okay, so basically if you are doing a measurement which is not full scale, you need to consider the limiting error because your error will be increased. Let's look straight at the example. You have a 600 volt voltmeter. Accuracy is plus minus 2%. So calculate the limiting error when the instrument is used to measure a voltage of 250 volt. So the manufacturer guarantee if you use 600 volt range, then the error is 2%. But no, you are now measuring not 600, you are measuring 250. So you need to do this calculation first. So the magnitude of limiting error is 2%, which is 0.02, multiplied by 600 equals to 12 volt. So then you need to divide 12 volt with 250, the value that you are reading, multiply by 100 to get 4.8%. Okay, so what does this mean? This means that for the 600 volt voltmeter, the error is plus minus 2%. But when you measure 250 volt, actually the error is 4.8%, not 2%, because the range of the value that you are measured is not the same as the value guaranteed by the manufacturer. And then another example, basically the same concept, a 500 milliamp ammeter plus minus 2% at full scale. Calculate the limiting error when you measure 300 milliamp. So basically you just repeat the calculation. So the range is 500 milliamp, you multiply by 2% to get 10 milliamps. And then 10 milliamps you divide by the range that you measure, 300 milliamps, to get the actual percent is 3.33%. Okay, this is limiting error. So you need to be careful when you do the measurement afterwards. Okay, the final part is the summation of error. Okay, so this will be the final part for today's lecture. So summation of error, the maximum absolute error is the sum of the two quantities and equal to the sum of the absolute errors. So what does this mean? You don't need to memorize, you just need to understand how to use. So let's dive straight into the example. Okay, given for a certain measurement, a limiting error for voltmeter at 70 volt is 2.143%, and limiting error for ammeter is 2.813% for 80 milliamps. So determine the limiting error of power. Now, for you to solve this, you need to understand about power. So you need to know this equation. P equals to V multiplied by I. Power is equal to voltage multiplied by current. So we have 70 volts multiplied by 80 milliamps is equal to 0.08 amps. So we get 5.6 watts. Because we use a voltmeter and an ammeter. Voltmeter to measure the voltage, ammeter to measure the current. So the voltmeter has a limiting error of this percent, and the ammeter has a limiting error of this percent. So when we want to calculate the power, we multiply V and I, and we add the limiting error for each meter together. So basically, this is what is meant by summation of error. So when we add them together, so the actual reading must be 5.6 with a tolerance of plus minus 4.956%. This is what is meant by the summation of error, the slide just now. So basically, when we have two parameters, each has their own limiting error, we add the limiting error together, either in absolute form or in percent form. Okay, so if we have a plus or minus operation, then we can add the absolute values. If you have multiply or division, then we can add the percentage of the changes of the absolute values. So that's why we have this addition here to get plus minus 4.956%. Okay, this is another example. So you have a 150 volt voltmeter and 100 milliamp ammeter used to measure voltage and current. Both has instrument accuracy of plus minus 1% full scale. So if the reading is for 80 volts and 70 milliamps, calculate the power and its limiting error. So now we have a combination of a limiting error and summation of error. So first we need to calculate 1% of the 150 volt, which is 1.5 volt. And then we divide with the measurement, 80 volts, to get 1.875%. This is for the voltmeter. And then for the ammeter, we get 1% multiplied by 100 milliamp, so we get 1 milliamp. 1 milliamp divided by 70 milliamp, we get 1.429%. So this is the voltmeter, this is the ammeter. So to calculate the power, we get 80 times 70 milliamps, we get 5.6 watts. And then the error, we add the percentage error from the voltmeter and from the ammeter to get 3.304% plus minus. And this is the summation of error. Okay, this is another example using power. A current of 2 plus minus 0.01 amps flows through a resistor of 100 plus minus 0.2 ohms. So calculate the power dissipated and the limiting error. So you need to know this equation. For power dissipated is equals to P equals to I squared R. So basically it's P equals to current multiplied by current itself multiplied by resistance. So the total power is 2 amps squared multiplied by 100 ohms, which is the value here. 2 amps times 2 amps squared times 100, so you get 400 watt. And the limiting error for the current is 0.5%, because 0.01 divided by 2. And the limiting error for resistor is 0.2 divided by 100, 0.2%. So since the equation we have P equals to I squared R, so we have I multiplied by R. So the error, we add them together, delta I plus delta I plus delta R. So we have 1.2%. So we can write the power dissipated as either in percentage, 400 watt plus minus 1.2%, or in absolute values, 400 watt plus minus 4.8 watts. Okay, so this concludes the topic on statistical analysis, error, and static dynamic characteristic of instrument performance. Okay, so the time now is 12:20, so just nice, 1 hour 20 minutes or so. So my lecture class session is over. I will edit this lecture afterwards and upload it in YouTube so that you can refer if you need to. And I now open if there are any questions or concern that you would like to raise. So I'm going to stop the recording now.